Good morning, champs. Now let's solve an entropy task step by step. We have two rigid insulated tanks containing nitrogen. Tank 1 is hotter at 480 Kelvin. Tank 2 is colder at 320 Kelvin. Both tanks have the same initial pressure. Now we connect the tanks and let them reach equilibrium. Physically, energy redistributes from the hotter side to the colder side until both reach the same final temperature. Because the tanks are insulated, no heat leaves the total system. Because the tanks are rigid, no boundary work is done. So we start with the energy balance. The change in internal energy equals heat plus work. But here, heat is zero and work is zero. So the total internal energy before equals the total internal energy after. For an ideal gas, internal energy depends only on temperature. That means the final temperature becomes a mole-weighted average of the two initial temperatures. First, we calculate the amount of nitrogen in each tank using the ideal gas law. For tank 1, we get about 45.0 moles. For tank 2, we get about 36.1 moles. Now we insert these values into the final temperature equation. This gives a final temperature of about 409 Kelvin. This makes sense because 409 Kelvin lies between 320 Kelvin and 480 Kelvin. Next, we calculate the final pressure. After opening the connection, the total volume is the sum of both tank volumes. So the total volume is 2.3 cubic meters. Using the ideal gas law again, with the total number of moles, total volume, and final temperature, we get a final pressure of about 1.2 bars. So in this example, the pressure stays the same. Now we move from energy to entropy. The entropy balance says change in entropy equals entropy transfer plus entropy production. Because the system is insulated, no entropy enters or leaves with heat, so entropy transfer is zero. That means the total entropy change equals entropy production. And since this process is irreversible, entropy production must be positive. Now we calculate the entropy change. For an ideal gas, the differential entropy change contains two parts. One part comes from temperature change. The other part comes from pressure change. When we integrate this expression, we get entropy change equals Cp times the logarithm of final temperature over initial temperature minus R times the logarithm of final pressure over initial pressure. Then we multiply by the number of moles. Now we apply this to each tank separately. Tank 1 cools from 480 Kelvin to 409 Kelvin. The pressure stays the same, so the pressure term becomes zero. That leaves only the temperature term. The entropy change of tank 1 is about minus 211 joules per Kelvin. This is negative because tank 1 cools down. Now tank 2 heats from 320 Kelvin to 409 Kelvin. Again, the pressure term is zero, so we use only the temperature term. The entropy change of tank 2 is about plus 253 joules per Kelvin. This is positive because tank 2 heats up. Now we add both entropy changes. Minus 211 plus 253 gives about plus 42 joules per Kelvin. So the total entropy change is positive. And because the system is insulated, this total entropy change is also the entropy production. So entropy production is about 42 joules per Kelvin. This is the key result. One tank loses entropy, the other tank gains entropy, but the gain is larger than the loss. That positive difference is entropy production. And that is why the process is irreversible.